Hi everyone, it's Mr. B here. What you're looking at is a cube that I just made up a 3 by 8 8 points matrix and projected this down onto the 2D screen. I'm using a program called Geogebra. So first thing to do, let's go and download Geogebra. Geogebra download Geogebra 5. The irony of Geogebra 5 for doing what we're doing is Geogebra 5 has now built in the capability. That's for Windows, Linux, all open source, all free. They've now built in the capability to do three-dimensional graphics, which means that all of the matrix operations and the projections are now built into this software. But we're going to do it entirely by ourselves, doing the projections by ourselves. So open up a new GeoGebra. Oh, because I said new, this doesn't come up with any axes. Here might come up with axes. You can turn them on and off. We don't need them here. I'd like you to have view, algebra, spreadsheet, and graphics in the middle, or whatever arrangement you like. Let's create a tetrahedron. 1 point at the origin. The other points we could make 1 unit away in each of the 3 dimensions. That would give us 3 points, each a distance of root 2 away. You could check that is correct. Okay, that's a tetrahedron. Easier than a cube just because it only has 4 points. Now, I don't want to create a list. I want to create a matrix over there. Matrix T. This is a tetrahedron. What are we going to do with this tetrahedron? We might rotate it, for example. Fix the x-axis. This will be a 3 by 3 rotation matrix. But I don't want to rotate it by something fixed. Let's take advantage of the sliders in GeoGebra. Make a few of these sliders. A, B, C, D, E. That should probably be enough. Let's make this one be a rotation by A, keeping the x-axis fixed. So cosine A, sine A, negative sine A, cosine A. There we go. We could do another one. Let's fix Z. And this one might be by B. B, sine B, cosine B. Make these into matrices. Go over here. It's on matrix now. That's good. R for rotation. Make this here. You can pause this if you need to catch up because you're not used to doing these things. Or maybe you need to put it on double speed. So there's a couple of rotation matrices. Other things we might do, we might translate this guy. Use C yet. We could make C be our new origin in the x direction. So that's C minus 1, C minus 1, C. We can make D be the y direction. You get the idea. D and D minus 1. We'll leave Z fixed. Problem is we still can't see anything. Another thing we could do, we could use E, for example, to scale this to make it bigger or smaller. We could just multiply E times R. But let's get to the question of how we're going to look at this thing, how we're going to see this. This is a tetrahedron. It's just in 3D, and we're on a 2D screen. So we're going to need to project it. Various things we could do. We could project it so that our new x-axis, we're going to have to take this 3 by 4 and turn it into a 2 by 4. 4 two-dimensional points. 4 ordered pairs in 2 dimensions. We could just make it so that the x and y axes remain, and we've just verify that the z-axis here is the null space of this matrix. There's no z anymore. That would be kind of unkind, though. We could at least use the number e to indicate how much z we're going to want, and so we're looking at it from a perspective where we have, well, actually we have quite a bit of z. This number e, we might not want it to go quite so. We certainly don't want it to be all the way up to 5. That would be looking at this thing very, very much from the side. It would be totally exaggerating the z component. So 0 to 1 is enough, or 0 to 0.8 or something, so we're not going over too much. And we can slide this guy back and forth, depending. Okay, so what we should have ideally is we should have a new tetrahedron, which we'd get from taking t, multiplying it by s, multiplying it by r, and then, oops, we need to actually create a matrix to project it. Multiply by p, s, r, and t. So we're multiplying t first by r, then by s, and then we're projecting it. There we go. That's our new n. That's our tetrahedron. These are 4 points. I wish I knew how to get this to just turn into points. If you find out, tell me. Right now I'm just kind of typing this in, which is kind of annoying. A is going to be n, first row, first column, comma, n, second row, first column. At least we can highlight these things and, you know, not have to change everything. So it's going to be first row, second column, second row, second column. That'll be point B, point C, first row, third column. I just have to make all these by hand. And D, fourth and fourth. Okay, there's our tetrahedron. Actually, it kind of looks like a tetrahedron without even, if you can imagine that. But we'd certainly like to connect these lines to make it look a little more. We don't have to paint the faces or anything just yet, but at least connect it. Beauty of a tetrahedron is you just connect. Notice I'm using the segment tool right here. You just connect all of the points. Well, we haven't connected D to E. I think I connected a couple of points twice, but it doesn't really matter. Geogebra is filled with all these tools, polars, locus, all kinds of things for geometry. Here we're just using the segment tool. So let's oops, get back onto your arrow. Highlight all of those. We don't want the labels to show up, and we don't need the labels for the points to show up either. There's our tetrahedron right there. We got our clicker. Let's see what D was doing. D must have been translating it in the Y direction. C is apparently translating the X direction. Notice that our perspective makes these things, they don't look perpendicular anymore. Rotating it a bit, that starts to look a little more like a tetrahedron. That's circling around right there because we're not on the axis anymore. Nice thing we can do, we don't need a spreadsheet view anymore. A nice thing we can do with all these numbers is we can now animate them. And there goes our tetrahedron. Oh, it's extremely jerky right now. We can look here on our preferences slider. Don't make it go by 0.1, 0.01 or 0.005 or something. And that should smooth it out a bit. If we're basically happy with how it looks, that doesn't look too bad. Let's slide it over so we can see it better. There you go. Obviously, we can change any of these things. We could have put a scalar in to make it bigger or smaller. But that's it.